Yes. Yeah.
So we will try to like code the gates and then see the simulation and create a test bench to test it. Okay, and then I'll show you the FPGA synthesis also, how it goes on the hardware. Okay, and there's like we focus just like the flow today.
Okay.
Okay, so there's a like create project is there, so we can do a create project and then next, and then I can say let's say we'll focus on the gate today. So maybe project name, maybe I give a gate. Okay, and then we can choose a location. Create option name on desktop. Let me create. I'll give you a name. Other way. Geez. So we can give a location to the project, which is uh, we- okay. The next, then this is a RTL project. Okay. So basically, what is RTL like? Register RTL's full form is register transfer logic. So basically, it's like a we say it's a coding. So it's like we start from the coding. So is this project start from the coding? So we say RTL project, and then is here like files are there. So there's no source currently, right? We want to create a source. So we don't want to add create. So we later create a file. Okay. So next.
Okay.
So basically, first of all, this language is there, right? Target language. Okay. You see here. So there's two languages, the VHDL, Verilog. Okay, so we will focus on VHDL first. Okay, and basically student start from VHDL, so that's why we focus on VHDL.
Okay.
So we choose the language VHDL, and next add constraint. So constraint also currently we don't have. We are trying to create. So let it. We'll learn later this thing
Okay.
constraint. Basic constraints are like let's say you have a hardware, right? It's hardware design. So how it will connect on the chip. This is a hardware, right? So you have to drive something, right, from the inputs. So how you drive those inputs and how you capture the output. So there will be pins on the basically on the hardware. So we map those pins of design to the hardware using the constraints. So how to map those pins, which pin to be connected to your input, your design input, that kind of things we write here. Also we write the clock constraint, like like design like what basically hardware is like for the speed, right? So what speed you want to run a hardware, and that gives a performance. So there's a clock is there. In each hardware will be having a clock.
Yeah.
So based on our design, we can we can like design a hardware which can run on different frequencies, right? With different clock frequency, basically 500 megahertz or 800 megahertz or 100 megahertz. And your
So,
design defines like how you design a design such that you can achieve a maximum frequency. It's up to you how you design.
so this clock we have to create. I mean, we have to create our own clock, or there is like inbuilt clock we can use. How that clock works?
Is there like oscillator is there on the board? There usually oscillator is there, so that gives you a reference clock. Okay,
Okay.
and then from the reference clock, there is like a PLLs are there in the FPGA. So you
Okay.
can choose a PLL to generate what clock you want to generate. Okay, but that clock there's a constraint. Other constraint like you generated a clock, but does your design can run on that clock frequency, that high clock frequency? It depends on how you design it, any design. So you can design. You can let's say I design some logic, okay, and you design the same logic. let's say you want to design a multiplier, let's say, okay, which multiplies the two inputs. Okay, you'll be having a C code, right? You multiply a unsigned int or 16 bit input to another 16 bit, it generates a 32 bit output, right? So that hardware you can create on the FPGA and you design a multiplier. So let's say I design the same multiplier which can run on the 500 megahertz, but you design the same hardware. Maybe it cannot achieve the frequency of 500 megahertz. Okay, so even the clock you have 500 megahertz, but until you achieve the frequency of your hardware, it will not work. It will misbehave. Like it will
Mm.
give you not correct result because it's not working. I will discuss that like those aspects later in the like
Okay.
once we go through like what is a clock, what is a registers and all. Okay.
Okay.
So this consent like basically we tell the tool like my design should run on this frequency
Mm.
using consent, and then the tool checks like whether your design can run or not that on that frequency, and then it gives you like the path of the hardware, which path is not able to meet your requirements. It will tell you, and you have to redesign or optimize your design to run on that frequency. And then devices are there, like a lot of devices are there. Like so, I said right, FPGAs also like we Xilinx manufacture FPGA. So FPGA also like hundreds of different types of FPGAs there. Some like based on the application, people choose like which board to run, and then definitely the cost is also associated with the FPGA. The bigger the FPGA, the advanced the FPGA, your cost will be more. Uh, so basically, based on the application, let's say somebody, some company or some company wants to design some algorithm on the hardware, and they know like what kind of like device they need to run that algorithm. So means that kind of things we before like planning, this is kind of planning
Yeah.
like you said right? You have to go to the banking, some banking company is there like and they do the algorithms like they design the hardware to run those algorithms. So that hardware is this is the name of the hardware. There's hundreds of thousands of hardwares are there. So you can choose one of the hardware basically from there. Let's say you have already a board, okay? Basically hardware is there. So you should know which chip is there on the which FPGAs are there on their hardware. Then you should choose that FPGA here so that your this tool knows like which FPGA you want to map your design, and
Okay.
accordingly it will. Basically, I can choose any as of now because we don't have anything.
Okay.
So let's small. This is quite a small FPGA because the number of elements like and flip flops and block RAM defines how small is the device. So you see, 14,000 LUTs only. You can go like some bigger devices like 53,000,
Yeah.
92,000, 1 lakh LUTs.
Mm.
So and the cost was also associated with that. Okay, I choose just this is an example. Right? Let's say I choose this. Okay, next and finish this creating project. Okay, so now you can see like your project is created, and there are different tabs are there, different blocks are there. So you can see the project manager is there. The I say type project name is gate,
Okay.
and there's the different sources are there like simulation source, constant source, design source. Since I did not added any design source, right? So now we have to create our own design. Okay, and you can see like this device we choose,
Yeah.
and then what language you want to so VHDL. Okay, so let's say we design. Now I want to create a gate and gate. Let's say so I create a gate. So I do the add source. Okay,
Mm. That's
and add since we don't have any file. So we what we do we create a source. Okay, create
mm.
and type is VHDL. File name we can give like and gate. Okay,
Yeah.
and then we can give any other location also. It will save to the local project, or we can choose a location itself. Let's say I choose this location and save here. Okay, okay, and get is created, and then default leave is this and finish. So here either you can add the port name here, or you can do later also while coding also. We don't choose anything here.
Okay.
Let's do here. Okay. So it's created a one source here and gate. Okay. And we double click it. You see your editor came.
Yeah.
So the three things are there in the editor. Three I can explain you. Like first thing is like, so first thing is like comments. Okay, you can comments are always using hyphen. Okay, two
Okay.
hyphens. So you want to comment in VHDL, you first do two hyphens and then you can write anything. That will be a comments. Okay, it's just a comment. This is automatically created by this tool. You can have your own comments. Anything is there. Anything is you can write here. Okay, but based on the like constant construct of the language. Okay, then that's come libraries. Okay, so this is these two things are like mandatory thing. Without this, you cannot execute your language. So this language needs library IEEE, and then this package in the library. This is must. You should must always use these two things to execute any VHDL file. And there different packages are there where different like, let's say I want to run a maths functions. So we do std underscore logic underscore arith dot all. So different functions are there. We can use that function, but as of now we don't need for this functionality those functions. Okay, that comes like definitely like how you have a C language, right? C language you'll be having inputs, right? And then so similarly here also input outputs are there. So input outputs, first of all the name of the functions. So name of the there you have a name of the function, here you have a name of the module, or name of the design, or name of the like whatever like hardware. So your hardware is AND gate. So I give a entity, and is a construct. This is must entity and is, and here you can define any name. This is AND gate. Okay, and then you must do a AND gate. Okay, this is like important thing. And in between you can write your ports. So let's write the ports. Okay, this is a comment, right? So comment is there, so that we can leave as it is. So uh, we have two like AND gate, like two input AND gate, right? So A B input and C output. Let's say, so we write input A. Okay, B underscore logic. So so one thing you understand, like uh, I was confused between Verilog and AJ. So A direction, and then in.
Give me 1 minute, Sandeep. I'm coming back. Just 1 minute.
Okay.
Okay.
So we write port, and then port will be like quoted in like this, and then A input, and then colon, and then in. So direction of the input. This is the input, right? So in std underscore logic. So std steps are coming by default in this tool. Okay, so std underscore logic is like a default logic in VHDL. So anything will be a STD logic. STD logic means there's a 9 types of logic is there, which is defined in STD. It's like a 0, 1, weak 1, weak 0, high Z, high impedance, and then X, U unassigned. Like 9 types of different logic is there, which is like a STD underscore logic in VHDL. Okay, so it means like you can assign a 0 value, you can assign a 1 value, or high impedance value, or a weak 0, weak 1, unassigned, X, don't care. Those kind of values we can give it to A.
So they
Okay.
what is the difference in that? Like if you say 0, 1 comparing with high impedance or low
So high
impedance?
impedance is like, like there's a buses like, uh, which is, let's say high impedance, we high impedance, we like, it's a logic, it's a current level in the hardware, such that you can drive any two people can drive, two drivers can be there, or multiple drivers can be there on the on that high impedance, because the voltage level is in middle, in between, between 0 and 1. So anybody can drive, multiple drivers is there, so there we use the high impedance.
So for the high current output, we have to use the high impedance. It is.
So we define just a Z high. So basically 9 types. I said 9 types of logic, right? So
Yeah.
0, 1. High impedance means Z. It's called Z. Z means high impedance. Okay. And then U is there. U means unassigned. X is there means don't care.
Hmm.
This is like literals, which is like we say like what is 0, what is 1, and then Z, what is U, what is X. Okay. So these
Hmm.
literals are possible values of A.
Okay.
And this definitely, in terms of hardware, in terms of current, this defines some current level or whatever.
Okay.
B. Then C is output. Okay. So out. C also one our output logic. Okay. Then it comes architecture. Okay. Architecture is like in between we can, let's say, uh, let's say you want variables, right? Let's say you let's say in C code also you have your inputs, right, and outputs. Okay. But to design that some function, you will be having some variables also, right?
Yeah.
So those variables we define here in between architecture and begin. Okay.
Okay.
So those variable basically defines like using signal. Okay. We say signal name. So let's say a int intermediate some signal, and this type is std underscore logic. Okay. But as of now we don't need. Let's This is like future use based on design. We in this logic we don't need any intermediate variable, because we can directly write this gate. Okay.
Okay.
So, and whatever logic we want to write, we will write between this begin and end. Okay. So
Okay.
what logic we want to write? We want to write a means get and get function, right? So and
Yeah.
get function is so there's multiple ways to write and get. Okay. So one way is like C. Okay. C assigns. This is assignment. Like
Okay.
how you do in C, you in the C language you do equal assignment, right?
Yeah.
Here you do like this. Okay. C assignment A and B. Okay. This is one way of the one way of writing the like a this is a means and gate. Other way, what will be, we can write like C assigns 1. Okay. So I said, right, here in C language you write 1 or 0 as it is, right? Here 1 we write like in the single quote. Okay. Or 0 also we write in the single quote.
Okay.
And if the vector is there, like let's say if the vector is there, so we write in double quote. Let's say 2-bit vector is there, we write in double quote.
Okay. If it
Single
is
bit we write in, or multiple bits we write in double quote, and single bit we write in single quote. Okay. So this is other way. So there's a like when else is also constructed in VHDL. So when C will be one, when both A and B are one, right?
One, yeah.
So A equal to one and B to one, else zero. Okay, this other way. So we can comment this as of now. Sorry, I said right. Cool. Between languages in Verilog, actually we can use uh,
Really like C.
without quotes. So
Mhm.
so now it's fine. Okay. So I can sometimes get confused between Verilog and VHDL. So
So
this
mostly, like you use Verilog, or how do you do that work?
so in beginning of career, we used like a lot of VHDL. So basically, and then now we are using Verilog. So it depends. Like US companies mostly use the VHD Verilog language, and now it's like it's not just Verilog. Now the system Verilog is there. It's like a next level of Verilog. It's called system Verilog. Mostly industries are using the system Verilog now. But it's like a upgraded version. Like Verilog, then you can definitely learn a Verilog.
Okay.
And his language is just a way of defining the things. If you know the design, you can definitely pick up any language soon.
Okay.
So there's two way of writing. Another way would be like, let's say you have a function, right, already let's say you have an and function defined in some file. Okay, then how you use, like you just use that function in the design, right? And then you can create. So here similarly, not the function. Let's say you have a hardware of and get, and you can instantiate that hardware here, and that is another way. That is called structural design. So this and get. So let me comment this. Maybe I want any both things we cannot have one way. Let's say this is the one way, and then we save it. So to test it, what we have to do, we have to have a test bench or test file, right? Test vector. So we go to the source and then simulation source. Okay. So we add a source. So we want to create a simulation source. Okay. And then create file. Then we say TB and gate. Okay. TB means test bench. Okay. You can give any name. It's just a name. And location. Just created a TB. Okay. So now TB is your, you see like three dots are there, right? Three
Okay.
dots are telling like uh, it's a top file. Okay. Top level file. Okay. So test, basically our test bench should be our top level file, right? Because that is driving the input to the design. Okay. So we make this as a top file. Okay. Set as top test bench. So this is created top. Now you see like and get is separate and this is separate. So but now we want to drive the and get, right? So we have to edit this test file so that it can drive it. Okay.
Okay.
So there's a file. So you can see like here separately a TB is there, but now TB is like a inbuilt, right? So TB will drive TB will be TB will, we don't drive TB, right? TB drives something, right? So if we don't drive TB or test bench, so definitely there will no inputs, right? Because TB itself is driving something. TB is not driven by something else. So TB will not be having any ports. Okay.
Yeah.
So what will be having? It will be having some internal variables, right, or signals, which will be used to drive, right, something. So I say signal A std underscore logic signal B. So it can be any name. Okay. Eh,
Hmm.
don't have a same. Don't need to have a same name, or you can have same name. Okay. The scope of this AB is limited to this file only.
Okay.
Okay. And scope of this AB is limited to this file only.
Okay.
Okay, so it's not like in C like global variable or nothing. Nothing is global here. Everything is limited to the same module only.
Okay.
Nothing is global.
Hmm.
Now I created some variables. Okay,
Okay.
so let me drive those variables. So what? So A and B we thought input, right? So you have to drive A and B. Okay, so and we can have some initial value to A and B. Okay, because there's an input. So initial values basically are given like this. Okay, we can initialize the variable there only. So let's say we want to give 0, to give this also 0. Okay, and and now we give our input. We drive those values. Okay, so we write process. Okay, in the process only we every sequential statement basically sequential means like it will be having a time to it. Okay, like it will execute one by one. So anything you write here, right? A assigns B, A assigns something, okay, or B assigns something. This will be executed together. This There is no difference between timing, like when they will be executed. Okay.
You mean they are not one by one. I mean,
Yeah,
it
yeah, they are not one by one. They will be executed together. Okay.
same time. Okay.
Okay. So we want like one by ones. Okay. And so process and process begin and process. Always end like this end process. Okay.
Okay.
And we write here like A equal to, let's say, 0. Okay. So now we give A and B value, we drive A and value, but we drive some time, right? We don't know how much time. Tool does not know how much time it has to drive, right? So we give some wait. Okay. So we do wait. Wait for how much? Some, let's say, uh, um, we can define here value nanosecond, picosecond, microsecond, both. Everything we can define. So wait for, let's say, 1 nanosecond. We can say nanosecond. Okay, 1 nanosecond.
So this wait is like the processing time for that gate, or what that wait is?
It will drive this value and wait here. It
Okay.
will on this statement. So I said, right, everything is sequential here, right? Okay. So it will assign 0. Okay. Then next it will assign this one. Okay.
Hmm. Okay.
Basically, it will not assign. It will schedule the assignment. Okay. Schedule until the next wait is there. So it will schedule the assignment until the next wait is there. Okay.
Okay. So the wait is because we want to get the two of the input at the same time. That's why we have to
Yeah, yeah,
wait.
yeah, yeah. So both the inputs will be assigned here at this wait. Okay. And then it will wait for this time here.
Yeah.
It will assign here. It will schedule assigned here. It will assign here. It will wait for this time. Okay, one
Hmm.
nanosecond. So what will happen? Like A and B value will be 0 for 1 nanosecond.
Okay.
Okay, and now we want to change the value A B. Okay, now let's say A. A, let's say A we don't want to change, we want to change B value. Let's say B value take 1, okay, and then again wait for same time. So what will happen, like one value B value will be scheduled to change, and it will change at this wait statement, and then it will wait for again 1 nanosecond. Okay, now we change the B value, sorry, A value we make 1. Then we change the B value to 0. Okay, so now all 4 possible values are there, right? 0, 0. We did not change 0, so 0, 1 will be there. Okay, we did not change B, so 1, 1 value will be there. And we did not change A here, so A value will be 1, and this will be 0. Okay, all 4 possible values are there.
So I
A,
have
B.
one question. So initially we have 0, 0, then we are waiting for that 1 nanosecond, right?
Yeah.
After that we are making it B2 1,
Mm.
then we are waiting for 1 nanosecond again.
Yeah.
So do we need to wait there? Because already A already has the value 0, right? So do we need to wait for that when we assign the
Yeah,
1
we
B,
have
right?
to wait, right? Because how we want to see the change, right? One, at least we want to hold the value of B to B for 1 nanosecond. Right? If we don't have it, so it will not hold the value, right? Or B and A will change together 1, 1.
Okay, so
We
for
want to
one,
first change the B value, right? For some time.
yeah, so for 1 nanosecond, it is B will be
1.
active high for 1 nanosecond. That's what it means,
Yeah,
right?
and A will be 0. Yeah,
Okay, okay.
A will remain 0 because
Hmm.
A will not change.
Okay, and the wait for 1 nanosecond, that is for the only for on the line number third when we are saying A equal to 0, B equal to 0, and third line wait for 1 nanosecond. So that is for the both of A and B, or that is just for the B?
That is for both. Both. It like both head.
Okay.
It is just a way. It's like it doesn't. Whatever. How many statements you can have before? It will for all assignments. Whatever all assignments are there, it will be done at that weight.
Okay.
And other assignment which is not changed, it will remain changed. It will remain unchanged. It will remain. It will be shown in the like uh, in your simulation. It will remain unchanged. Any change will be assigned at the weight or at the end of process also. Okay. So what will happen? Like it will do again, and it is like a sequential process. It will continue, come again here. It will do it. It will in loop. This continuously. It will keep doing it.
Okay.
So how long you run the simulation, it will keep doing this. So now we have A and B, right? So I said, right, this A and B is limited to this, okay, and this A and B is limited to this file, okay. But how we connect it now, okay? So we have a method to connect it, or so what we do, like this is a design, right? This is a unit, or this is like a hardware. So or we can say it's a component, okay. We
Hmm.
have, right, different. Let's say you build a breadboard, right? So you will be having a AND gate component
Yeah.
and OR gate component. So like this is also a component. So there's a component construct is there in the VHDL. So we use that construct as a component. So we copy this. Okay, I'll tell you what is a component. Okay, just copy this and paste here. And entity will become component. Now entity it was there. Here it will become component. Okay, and end component. Okay. So now see the port will remain same. So now this is different. This we expose this component in this way, but still we did not connect this A and this A. This A is local to this component, and this A is local to this file. Okay, still connection is not done. It's just a component defined. Now we have to connect it. So we have to connect here in this begin. This begin to this end. We have to connect anywhere you can. You can write here also. You can write here also. Okay. We
Okay.
connect here. Just copy it. Okay. So this is called port map. So we define instance I. Let's say we can and get. Okay. This is the instantiation name. Okay.
Mhm.
I and get. You can give any name, like just a name. Okay. So what is the name? And get. What we are instantiating? And get. This is the instantiation name, and what we are instantiating? And get. And now we do port map. We do port. We say port map. Okay.
Yeah.
Instead of port, here we map it. Okay. How we map it? And A will be mapped to A. So A mapping is like this. So you see assignment is like this side arrow, and mapping is this side. Okay. So
Oh.
A will be, so this A is look A is port of this AND gate, and A is mapped to the A of let's A of this file test bench. Okay. A is mapped to A. B is mapped to B. C is mapped to C. Okay. The mapping is done. Okay. So now your code, so you see there's no error. Green is there, means no error is there. Okay, in the file. Now we can run it. Okay. So we save it. So now you see, now I'll show you the project. Okay. As we instantiated it, you see the AND gate was outside here earlier. Now it will show in the hierarchy. So you can see the hierarchy here in the project, right? So
Yeah.
let's say you have multiple modules and they might be instantiating in different hierarchies. So all the hierarchies can be seen here, like which module is instantiating which function or whatever. So currently TB is instantiating the AND gate, okay? And
Mhm.
what is the instantiation name? I and AND gate. I and gate can be any name. You can give any name here.
Okay.
So it may not be I and gate. You can give just I also is possible.
Mhm.
Okay, so this instantiation done. Now we run it. So you can see here run simulation is there. Okay. I just click it. So what it does, run step will elaborate your like code and it will create a simulation function. So you see the as soon as we run it, so it opens some other things. So it's showing the object. Okay, what object is there in the test TB? ABC objects are there, and then protocol instance thing is there. So and then this is the waveform. This is called waveform. Okay, so you
Mhm.
see the one waveform is open,
Yeah.
and uh, so object in the TB gate is A and B C, and the object in I gate also A and B is there. So you see, right? A and B is I and B is O. Okay, and while the object in the TB is not input or output, it's just a signal.
Okay.
So there's nothing written. But object in the I and gate A and B is I because input and C is output.
Mhm.
It could have been different. If I would have given different name, so here it would be written like A. That name of signal in TB, it will be different name here. Okay. So
Yeah.
currently you can see the waveform. So waveform is showing by default. The waveform will open with the signal defined in the TB. So all the signal which is defined in the TB is showing here. Okay. Let's say we want to see this signals also in the our test bench. So I
Yeah.
just select this and then add to wave window. So you can see like A, B, C is also added. A, and Z. So you see like A and B is same as this A and B because we connected it right in the TV. So they must show the same value on the A and B, this A and B and this A and B because we have connected it. And whatever the C output is there, C also should be same as both. Okay, because we have connected it, so they must show the same value. on this
Okay.
port and on this also.
Mhm.
So there's a run is also there. Uh, so here we can do run. Okay, run for let's say 100 nanosecond. Okay, not 100 is too much. Maybe 10 nanosecond. Okay. So it run for 10 nanosecond. Okay. So now I zoom it. Okay. So I just zoom out. So you see like, okay. So now how it's appears, right? First 1 nanosecond, right? I given the zero value, right? So you see at 1 nanosecond, the value of A and B is what? 0. Why it's showing 1000?
Okay, so that initial two black box, that is 0 0, then B is becoming 1.
Yeah. So you see when 0 0 is there, what is the C output? A and B is 0, C output is 0 because
0.
0. And when this is 0, this is also 0, right?
Yes. Yeah.
When both are 1, then only C is 1. Okay. When here also it's 0, right? So this simulation, it's showing the simulation. Okay. One more thing, I'll just show you like I've written two different code, right? So let's say I commented this now. Okay.
Mhm.
I uncomment this. Basically, it should show the same behavior, right? So waveform should not change because of the same behavior. Okay.
Okay.
So I just join it and we rerun. So basically, we run simulation again. Run behavior simulation. So it's showing like behavior function simulation sim set. Already, do you want to close the simulation relaunch? Yes, we want to relaunch the simulation.
Okay.
You see, same thing, right? 0 0 0 1 0 0 1 0 1 1 1 and 1 0 0, right? So behavior remains same because there can be a different way to write the logic and then we see the same results.
Mhm.
Okay. So now this is one aspect like simulation, you understand, right? How we simulate it. Okay.
Yeah.
So now in the same tool, I'll show you, maybe we can close the simulation. Okay. So now how we map it to the hardware, right? There's a other aspect is also there, right? So there's like implementation is there. So there's four steps are there. RTL, as we do simulation, right? RTL is already analyzed. Okay. Means basically code is already analyzed. Okay. So this
Okay.
step is already done in simulation. Okay.
So RTL we do not do separately.
Because to do simulation itself, it has to be elaborated, RTL elaboration. Okay. So this step you can run if you run this step, you don't, I mean, if you run this step, you don't need to run this step. Okay. Automatically run. So you said, see, it's showing the open elaborated design is already done.
Okay.
If you don't run this step, let's say I change something here. Let's save it. Basically, okay. So see, it's again started doing elaboration because elaboration was not done, right?
Mhm.
Because I changed the value, so it is doing elaboration. It's very quick. So what it will show you, it will show you the like actual hardware how it is implemented. Okay. So
Okay.
what we implemented a gate, right? You remember in the design.
Yeah.
AND gate. So it's showing like A, B and AND gate, and this is C output. Right? So this way you can see in the elaborated design, it will show you like in terms of diagram from your code. It will show you in terms of gates, basic element basically. So you see like leaf elements are there. Like what is a leaf element? Leaf element is leaf cell is a gate. Okay, so whatever you write a code and you do open the elaborated design, it will show you some gates, some registers, flip flop basically flip flops. Those things it will show you.
So
And
this use of RTL is to create the structure like this diagram. That's the use of
yeah,
RTL.
use of RTL is a language. And so was it basically what you might have done some like in electronics labs, right? Some circuit design using the gates and
Yeah,
wires, right? You do some basic logic you write there, right?
yeah.
So same way, the language is there. So language can do the same thing for you. You write the same similar maybe very big logic, and then the same logic will be implemented using the basic elements, right? The basic elements is what? Gates, registers, memories. These are the basic elements. So those basic elements will be used to create your design. So at the leaf level, what will be there will be many basic elements, and that will be connected each other, right? And that will be that you can see like whether your design is, let's say, you created a like Verilog code or a Visual code, and then you want to see whether your like design is really what intended to write is creating the similar design or not. You can see this gate level like diagrams. Okay, this is
Mhm.
just a elaboration. So it's from the RTL to this. Okay, now to map on the hardware, more steps are there. So how to map on the hardware? Okay, so there's like synthesis there. Okay, synthesis, what synthesis does, like it takes the elaborated design, and then it maps to the like like FPGAs are having basically the LUTs and RAMs, and then registers, multipliers, lot of things are the basic elements are there which is designed on FPGA. So synthesis maps your the gate level design, or you can say RTL, to the element of the FPGA. So the synthesis does that thing. So mapping from the code to the elements of the FPGA. Okay, I run a synthesis.
So it's an automatic process.
Automatic process. Yeah.
Okay.
So any issues are there in the design, then it will show up the synthesis process. Okay.
So,
You see here is doing icon corner. You can see the running synth design is doing the synth design.
so this need to be connected to the hardware, or without hardware connection
See,
we can.
this everything can be done without hardware.
Okay.
But at last to run on the hardware, you definitely need a hardware. If you want to see the same function on the hardware, you have to have a hardware. But this step can run without hardware. This tool can run without hardware. So this process done. Synthesis done. Now implementation. Implementation is basically this mapping is done, right? So like in the some elements. Now implementation, what will like this? Let's say I have chosen only one gate, right? This is only one gate, but your FPGA is quite big, right? So you have many AND gates, right? Where to implement this AND gate? So
Okay.
the implementation will do that. Where to map it on the actual hardware, location of the hardware, pin of the hardware, where to map it. The implementation does that. Okay, so I just run the implementation, and it automatically it will map it. It might give an error also, because it may say like you don't have a constraint where to map A and B and C. You not tell me. Maybe by default it may map it. I'm not sure. Give error or not. It may give warning maybe because there is no constraint design now. So it is doing the mapping automatically.
Okay. So you said that for the implementation, we have to say where that AND gate is implemented, right? Like what part?
Yeah. So that's what I'm saying. Like uh, it can do automatic. It can map anywhere.
So like, yeah, but so that we can also do it manually, or we have that
Yeah,
software.
manually also we can write in the constraint like which AND gates to pick up. It will do that. Okay, so we don't need to like we can say also we can define it in that is a that I say right constraint file. There we can define like this AND gate to map where. Currently it has automatically mapped anywhere. Whatever tool can do anything for you and it's mapped anywhere. But basically you can also say uh, and now the implementation is now is the generate bit stream. So we don't want to open this. We just want to generate bit stream like it is a file which will be generated, a design file basically related to your design, and that bit stream file will through the hardware. Let's say you connect you connect. We will be connecting your hardware using a cable to the laptop, and then this bit stream will be going through that wire to the hardware. It will program it. So that bit stream is a programming file which will program the hardware to like your design. So generate bit stream is a step to generate it, the bit stream. So I said just generate it. So it will be generating the bit stream. Okay, write bit stream, running write bit stream. So it's writing a bit stream file which will be used to program the hardware.
Oh, so this is the last step when we put all these
Yeah,
files.
last step of the tool to for the like design related step. Next is running on the hardware, but we don't have hardware, so we cannot run now.
So we do all the development and testing on the using the software, and at the final stage we put that code in that FPGA,
Yeah,
right?
yeah,
So,
yeah. So piston generation failed. Uh,